Okay, good evening. It's good to see you again. So today we're going to do modular arithmetic. It's called clock arithmetic. Has anybody seen that before? It's not a standard topic, but sometimes people learn it. And it's used in computers a lot, so it's a very nice thing to know about. But first, what we're going to do is we're going to review set theory. And the topics that we review in set theory, we're not really going to use them today, but we will use them tomorrow. So we're going to look at a review. Hilbert's Hotel. Yes. Hilbert's Hotel is the best. Okay. Oops, that's tomorrow. Review of set theory. Okay. So if all we ever had were finite sets, it wouldn't matter. Set theory wouldn't be much of interest. But it's when we get infinite sets that things are interesting. And the standard infinite set, which is called the countable infinite set, infinite set, is the counting numbers. And the cardinality of this set is Aleph naught. We talked about that yesterday. And so we say this is countably infinite. This is how we talk about it. And when we have an infinite set, we cannot count the elements like 1, 2, 3, 4. In fact, this set, I can't do anything except list them. I just go 1, 2, 3, 4, 5, 6, ... That's the best we can do. But Cantor developed a technique, and this is how Cantor... this is the main tool that Cantor gave us for dealing with infinite sets, because we can't deal with counting. So Cantor said two sets have the same cardinality if there is a one-to-one correspondence between them. So a one-to-one correspondence, let's see, I'll try to write that a little better. It's 1-1, a one-to-one correspondence between them. And what that does is it pairs the elements up. It's the analogy I used of a classroom with chairs. If all the chairs were full, there were no extra people, you would know that there were the same number of chairs as there were people. Now I'm going to look at these two sets, and yesterday I called these the natural numbers and I called these the counting numbers. And I said that different people said different things. They give them different names. In fact, I know another mathematician who insists on calling these the natural numbers and these the counting numbers, but that's why I'm not too concerned with what they are. And another reason I'm not too concerned with the names is because they have exactly the same cardinality. I'm going to do a one-to-one correspondence, and the rule that I have here is I take whatever number I have here and subtract 1 if I want to go this way. So here I subtract 1, and if I want to go this way, I add 1. So I know there's a perfect one-to-one correspondence. So we say they have the same cardinality. And what Cantor said was that the rationals had the same cardinality. Let's see. The cardinality of the rationals is the same as the cardinality of the natural numbers, which is Aleph naught. And we saw how to do that with the grid. And in fact, we're going to do some more Hilbert's Hotel problems, and we'll see that we can, well, we'll review this. And we also saw that the cardinality of the real numbers was not the same as the cardinality of the natural numbers. And because we could always find more real numbers than natural numbers, we can actually say that it's larger. Okay, so these are two very important things that we did yesterday, and we did them by, we showed them by one-to-one correspondence, either finding one or not finding one. Okay, now let's go back to Hilbert's Hotel. Where are Hilbert's Hotels? Are they here? Can't remember. Oh, okay, here we go. Oh, here we go. Okay, so let's look at Hilbert's Hotel again. So Hilbert's Hotel has infinitely many rooms. And there's countably infinitely many rooms. So Hilbert's Hotel has a room for 1, for 2, 3, 4, 5, like that. So this is countably infinite. And we saw that if we rearranged the people in the hotel, we could do a lot of interesting things. And the first thing we did was we saw that if the person in room 5 moved out and the person in room 12 moved out, that we could move the person in room 6, goes into room 5, so the person in room 6 goes into 5, 7 goes into 6, 8 goes into 7, 9 goes into 8, 10 goes into 9, 11 goes into 10. But then when we get to 13, what happens is 13, there's now 2 rooms open, 11's open and 12 was open. And so 13 has to go to 11. And then we everybody after that moves down too. So the idea of Hilbert's Hotel is there's infinitely many rooms. Now, here, everything looks okay, and there were some concerns about what happens way out here. Is there a last room? No. Is there a room numbered infinity? No. Because what we have is we have this list, 1, 2, 3, 4, 5, 6. It keeps going on. Whatever room you're in, maybe you're in room 1000, there's a next door room. And we know this from the way the numbers are structured. Not if we were using Roman numerals. Roman numerals, they go up to 100,000. They probably have symbols after that. But here we can, whatever number we have, we can get another number. So that's how this works. Okay, so let's see. There's two that we didn't do yesterday. Okay, oh, we didn't do that one, but that one's just like the one before it. Okay, now. Oh my gosh, this is the Galaxy Games, the Galaxy Olympics. We have infinitely many tour groups, which is nice. We're going to have a lot of people. And look at what happens. Each one has infinitely many guests. Now, if you had one tour group with infinitely many guests, you could put them in there. You wouldn't have a problem. But now we have infinitely many guests in each of infinitely many tour groups. So what we have here, the guests are numbered 1, 2, 3, 4, 5 forever. The tour groups are numbered like that. And so what we're going to do is we're going to do a pairing the way we do on the Cartesian plane. We're going to give each person not one number, but two numbers. So the first number will be the tour group number. And the second number will be the member number. Okay, so that's how we're doing it. And now, how are we going to fill up the hotel? Well, the first step in assigning rooms is to make sure we have everyone accounted for. So what I'm going to do is I'm going to do tour group 1. And list all their members. Okay. So we've got this list of tour group 1. Then I'm going to list tour group 2. First person in tour group 2, second person in tour group 2, third person, fourth person, fifth person. Of course, I can't list them all. There's infinitely many, so I have to have a pattern. Third tour group. Now, this is only what the physicists call a thought experiment, because we've never seen anything like this in the real world. And I kind of hope we never do. It could be hard to deal with. Okay. So now, who's going to go in room number 1? Let's put this person in room number 1. Then we can't just keep going down this line because we'd never get to tour group number 2. We can't go down this column because we'd never get to the second person in each of these groups. So what we do is let's see, this person gets the first room. And I'm doing one possible way, and you could come up with another way. There's many ways, but the idea is to kind of be like a snake and snake through this. And we're not going to worry about the fact that it's going to take an infinite amount of time to assign all the rooms. But you see that if we follow this route, everybody will get a room and every room will be filled up. Okay. So that's how we can do this. We keep everybody happy. We keep the tour group people happy and the manager happy because all the rooms are full. Okay, now what has happened here is there's an intergalactic, that was the Galaxy Games. This is Intergalactic Society of Irrational Space Cadets. And it's only one group of people, but each person has a non-repeating, non-terminating decimal. Oh, okay, I've got a question about this up here. This 1, 2 here, 1, 2 means tour group 1, person 2. Down here, tour group 4, person number 2. Okay, that's how I did that. Because I have to be able to make sure I've covered everybody in all the tour groups, every tour group, every member. So I give them pairs of numbers. Okay. Okay, now the manager is afraid that finally the hotel has reached the limit and will not be able to accommodate them. And the hotel's empty, so that's nice. So now I kind of gave you a hint here with this irrational in here. And this is exactly the same as the problem where we tried to find the cardinality of the real numbers. And this is the hardest thing we did yesterday. And this is actually the hardest thing we're going to do in the whole 4 lessons. So what we do is we suppose we have an assignment. Okay. So the tour group comes and they say, well, we're going to put this here's our list. And they're irrational. They don't repeat and they don't terminate. So I can't do much here. I can just suppose I have something. I'm just making up numbers here at random. But suppose there's an assignment. Like that. So these don't repeat and they don't terminate. Okay. And we're saying, suppose we have an assignment. Well, the manager looks at our list, and the manager says, well, you can't have all the people because I'm going to look at these numbers. And this is called Cantor's diagonal proof, because these numbers go down the diagonal. And we're going and okay, the thing is with this, we have a procedure. If I just gave you a number I thought was not on the list, that wouldn't help because you could change the list. But I have a procedure. If I'm the manager, I have a procedure that's going to handle all possible lists. So one of the things about techniques in mathematics, we want to handle all possibilities. Same thing in computer science. If you write a program, you want it to be able to handle all possible inputs. Otherwise, you don't know what's going to happen. So what we do is we come up with another number. I'm going to say, well, what about 2, 7, 3, 5, 8, 2, okay? Now you could have come up with a different number and that would have been fine. Because not only is this one not in the list, there's infinitely many things not in the list. Way more, there's more things not in the list than are in the list. Now, why am I so sure that this is not in the list? Because it's different from the first number. It's different from the second number. It's different from the third number. It's different from the third number in the third place. You know, it might have been the same as the first number and the second number in the first two places, but it's different in the third place. This one and this one are different in the fourth place. So for two numbers to be different, all you have to do is show they're different in one decimal place. Then they're not the same number. Okay? So here's what you have to tell the manager. You have to say, manager, I cannot do it. There's way too many people. Okay? So we're going to see another example of this tomorrow. And it's actually an example that Cantor came up with as well. So that'll be kind of nice. Now, what we're going to do, I think this is all the review that I want to do today for this. And if we have time at the end of class, we can do some more review. But we're going to look at a clock, and we're going to do clock arithmetic. And if it's 2 o'clock, then 5 hours later, what time is it? It's 7 o'clock. That's easy enough. If it's 7 o'clock, what is it 10 hours later? If it's 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's going to be 5 o'clock. Okay, so in clock arithmetic, 2 plus 5 is 7. In clock arithmetic, something else happens. 7 plus 10 is 5. So we're kind of amazed by this. But if we think of a clock, no problem. 7 plus 10 is 5. If it's 3 o'clock, what time is it 12 hours later? Well, it's still 3 o'clock. So, in fact, if we wanted to, and mathematicians want to, other people don't, but mathematicians would rather a clock had a 0 here instead of a 12. And that's because 12 acts like the number 0. Okay. So this is clock arithmetic. And right now you're probably thinking, well, yeah, clock arithmetic, no big deal. You do it all the time. But what we're going to see is that a lot can come out of using clock arithmetic. Now, what I'm going to do, we're going to do clock arithmetic. We're going to do an addition table. And you should understand, you know, what I have here. This is 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, like that. This last column's just here by mistake. You should have a spreadsheet that I sent to you. Do you have the spreadsheet? Did everybody get that? Good. Okay, people are saying yes. Good. If you don't have the spreadsheet, you could make one of your own on grid paper. But it's a lot easier. You've got the grid already. So let's see if it's, well, we've got some of these already. If it's, this is going to be first. And this is going to be second. So if it's 3 o'clock, what time is it 4 hours later? It's 7 o'clock. So we're going to put a 7 in there. If it's noon, 12 hours later or 0 hours later, it's still noon. If it's noon, 1 hour later, it's 1, 2. Okay? So what I would like you to do is fill out this table. Do you have enough information to fill it out, or do I need to say more? Okay, yeah, raise your hand if you can fill it out. Good, 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 good. Okay, so take some time and fill it out. You know what I'm going to do? I'm going to stop sharing, and I'm going to fill it out. Because I don't want you to see me filling it out. I want you to have a chance to fill it out on your own. Okay, how does that sound? And then we can compare answers. Now, one thing about filling this table out, you know, you've been doing addition all your life. You can use those rules, but you have to remember we have a clock with only hours from 0 to 11. So no number in the table can be bigger than 11. But the other thing is, and this is what helps mathematicians all the time, is you may see a pattern. And if you see a pattern, you can use that pattern so that you don't have to do a lot of work. I mean, I realize adding 8 and 8 is not a lot of work, but you know, you have to think, well, what's going to happen? 8 and 8 is 16. Well, 12, if, you know, 16 o'clock, well, that would be 4 o'clock. So you can use, if you notice any patterns, you can use those patterns. I just made a mistake myself, but when I was looking at the pattern, I could pick out that I had made a mistake, so it was easy to fix. Okay, so, some people are saying, please share the screen. Well, you know why I'm not sharing the screen? It's because I was figuring out the answer and I wanted you to figure it out on your own without seeing my answer because, anyway, okay, so somebody's done, finished. If it's bigger than 11, reduce it by 12 points. Is this a pattern? Absolutely, that's a pattern. So if you add 7 and 7 and you get 14, then just take away 12 and you get 2. So 7 plus 7 is going to be 2. Okay, so lots of people are done. So let's go back to sharing. And let's see, I got to make sure I can see the chat here. Okay, does anybody see a pattern? Okay, now there's tons and tons of patterns in here. Probably tons isn't the right word. Every pattern is abstract, but there's lots and lots of patterns in here. Does anybody want to say something about a pattern? Okay, patterns diagonally. Beautiful, beautiful, beautiful. So I'm assuming you mean like this. This is a diagonal. Okay. Now, in mathematics, anytime you see a pattern, there should be a reason for it. And the reason for the pattern is deeper than the pattern. Knowledge has organizing power. The pattern was organized by knowledge. The knowledge of the pattern is deeper than the pattern, and it's more powerful than the pattern. It's a principle rather than a detail. So the whole is more important. Now, okay, so then why is 12 equal to 0? There's a question in the chat. Well, it's because we decided that 12 was going to be like 0. Well, we didn't decide it. That's how clocks work. If it's a 12-hour clock and it's 3 o'clock, 12 hours later, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hours later, it's still 3 o'clock. So why use 12 when we can use 0? We understand how 0 works, and so let's just use that. And okay, 11 plus 8 is 19. Okay, 11 plus 8, where's that one here? 11 plus 8. Well, of course it's 19 in regular arithmetic. It's also 19 hours. But if we start at the top and go around 19 hours, we get to 7 o'clock. So if it's 11 o'clock and we go 8 more hours, we get 7 o'clock. So, and then we write this. We have a way of writing this. We will write 11 plus 8. Now, we don't want to write 7, okay? I mean, we do want to write 7, but we don't want to write 7 because if our friend walks in the room and we wrote 11 plus 8 equals 7, they'll say, what kind of crazy school are you going to? So what we do is we always say how we're doing it. We're doing it mod 12. And we don't want to write equals because that is really going to confuse things. So we say 3 lines like this. It's kind of like equal, but we call it equivalent. So we're not going to say these are equal. We'll just say they're equivalent. Okay. And I'll tell you why the diagonal works. Let's look here and here. What happens going from here to here? Well, this number decreases by 1 because we have 4 plus 7, and this increases by 1. So 4 plus 7 and 3 plus 8 better be the same number because here we went down by 1, here we went up by 1. The net result should be the same. So that's why diagonals are the same. Okay, now, this is, congruent. Yeah, this is the word. Somebody's got this in the chat. We can say equivalent or we say congruent. Congruent. This is modular arithmetic. And okay, now you thought you were okay. Maybe that was fine. Now we're going to do multiplication. This is definitely harder. Although we can have patterns. What is 0 times a number? 0. Okay, somebody got that really fast. 1. I'm just going to put zeros all the way across. 0 times anything is 0. I don't have to think twice. What's 1 times let's just say x. What's 1 times, okay, 1. 1 times 1 is 1. 1 times x is x. So 1 times 2 is 2, 3, 4. This one's easy. And you notice I'm doing the column at the same time because I see, you know, like, think about it. There's 11, no, there's 12. There's 144 numbers I have to put in here. And I really want to make it go quickly. Some of them are going to be easy. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. Ah, okay. Okay, somebody's saying 12, 14, 16. Okay, 2 times 5 is 10. 2 times 6 would be 12, but what number do I write? I can't, yes, good. I'm going to write 0. I can't write 12. And then 14 is 2, 4, 6, 8. I'm seeing a pattern. Okay, do you see the pattern there? That was Uvinda. And then 3 times 6, 9, 12, but that's 0. And you know what's going to happen here? Because what is multiplication? It's repeated addition. So we can just keep adding 3. So we add 3, 3, add 3. We add 3 to 9 and we get 12, but that's 0. 3, 6, 9. 4, 8. Now we get 0. Add 4 more, back to 0. We see a pattern. And you know what else I'm seeing here? Look at this pattern. What do you think is going to happen here? 11, 10, 9, 8. I bet it's going to be 7, 6, 5, 4, 3, 2, 1. And I bet this is going to be 11, 10, 9, 8, 5, 4, 3, 2, 1. Okay, 5, 10. Oh, this isn't going to be so nice. 15, but that's 3. Add 5 and we get 8. 13 is 1, 6, 11. 16 is 4, 9. 14 is 2. That was a mess, but, you know, what can we do? 6, that's going to be easy. 6 plus 6 is 12. That's 0. Okay, and you know what? We can, multiplication is commutative. Okay, that means it doesn't matter which order we do the numbers in. Somebody's in the chat saying 10th column is going down. Oh, that's interesting. 10, 8, 6, 4, 2, 0. Probably is going to be 10, 8, 6, 4, 2. Good. And then the zero's up at the top. So maybe it's going to go this way. This is commutative because 10 times 2 is the same as 2 times 10. 8, 6, 4, 2, 0, 10, 8, 6. Good. Okay. 0, 9, 6, 3. 0, 9, 6, 3. 0, 9. I'm really lazy. 0, 8, 4, 0, 8, 4, 0, 8, 4. 0, 8, 4. 0, 6, this one is the nicest because 6 is half of 12. Okay, oh dear, 7's not going to be fun. That's going to be 7 and 7 is 14. So, and then 7 is 9. That one's easy. 7 and 9 is 16. That's 4. That's 11. 7 and 11. is 18, so that's 6, and that's 13, so that's 1. And 8, it's 480, 480, 480. Nothing says we have to go in order. 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 3, 6, 9, 3, 6, 9, 3, 6, 9. Of course, the 0. 0, 9, 6, 3, 0, 9, 6, 3. And I'm done. Okay? Now, this has patterns too, but they're subtler. That main diagonal just we saw, there's nothing with the diagonal here. But what we do see, I can't count the 4 here. We see things that match up across this diagonal. If we go across this diagonal, things are equal. And that's because of commutativity. Okay, now we could, okay, 6 times 6 is 36. Where's that? 6 times 6 is 36. Why do we put a 0 there? Well, because if we have a clock and we go 12 hours, we've got 12, 12, 12, and so we're back to 0. So that's how we get that. Okay. Now, I have a question for you. And when we were doing this, when we had a pattern in a row that repeated, it was nice because it was easy to do. And what I'm going to do is I'm going to look at the rows where we have a repeating pattern. Here we repeat. It takes 6 before we repeat. It takes 4, 3. This one doesn't repeat. This one repeats. This one repeats. This one repeats. And this one repeats. So the question I have for you is, what is special about the rows where we have repetition? So the numbers where we have repetition are 2, 3, 4, 6, 8, 9, 10. What is special about those numbers? Okay, somebody says odd and even. Absolutely, it has to do with odd and even. But what we see is that, well, all the even numbers are there. But there's some odd numbers thrown in as well. Okay, prime numbers. Well, some are prime. 3 is prime. Yeah, 7 is prime too, but it didn't repeat. The repetition, yeah. Okay, so some are prime and some are not prime. Now, you're suggesting very, very good ideas. And by that, what I mean is you're coming up with things that you can check. So somebody said even. Well, yeah, all the even ones have repetitions, but so do some odds. And then somebody said prime. And some prime do and some prime don't. Somebody says it's an algorithm. Well, yeah, sure, it is an algorithm. And we're trying to understand what the algorithm is doing and telling us. Okay, so, okay, all have zeros. Okay, now this is okay. Somebody, Kanishka said, I don't know if I'm pronouncing the names right, that all of these have a 0 in them. Well, of course, they all have the 0 in the beginning. I'm not going to count that. Everybody has a 0 in the beginning. But, oops, that's not a 0. It has a 0 somewhere in the row. So they all have zeros. This is a beautiful observation. And then somebody else is saying all the numbers can divide by 0. Divide 12. Well, they can't go into 12, but what can we say? 2, 3, 4, 6, 8, 9, 10. There's somehow those numbers are related to 12. Let's think about it. Because this observation, they have zeros. The ones that don't have patterns never had a 0. I mean, they did at the beginning, but 0 times anything is 0. Of course, we don't, that's nothing special about anything. But when do we get a 0? Let's look at some of these things. 2 times 6 equals 0. 3 times 4 equals 0. Okay, I'm interested in the 2 and the 3 and the 4. 4 times 3 equals 0. And then we have 6 times 4 equals 0. We also had 6 times 2. And then 8 times 6. And we had 10 times 6 equals 0. Okay, we have the answer here, Madhava. It has same factor as 12. Okay, so if we had 2 over 2 divided by 12, 3 over 12, 4 over 12, 6 over 12, 8, 9, 10 over 12, we could reduce the fraction. So these numbers, these are special numbers, 2, 3, 4, 6, 8, 9, 10, all share a factor, and I'm going to have to say that's different from 1 with 12. Beautiful. So that's the pattern. That absolutely is the pattern. And if we had discovered this, this would be our first theorem. This is so important. So important. Okay, now what I want to do, you know what, I'm going to do something really easy first, just because, don't look at this part, just look at this part. I want to do this because it's going to be easy, and then I'll have you do something harder. So let's fill in this. Okay. Mod 2 arithmetic. Let me explain. One of the themes in this course is infinity, and a clock is not very infinite. But the thing is, we're going to have infinitely many clocks. So we're going to have clock arithmetic for every number, every single number. So here's a clock with 2 hours, 0 and 1. It's going to be easy. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1, what's 1 plus 1 going to be? Okay, I've got somebody. 0. Good. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. Okay? So what could be simpler than this? And you might say, well, who cares? You know, this isn't very interesting, just 2 hours. But this is actually used in computers all the time. And oh, let me just say about this. 1, of course, is 1 mod. This is mod 2. 3 is 1 mod 2. 5 is 1 mod 2. 7, 2, 4, 6, 8. So odd numbers are 1 mod 2, and even numbers are 0 mod 2. I should have started out with 0 here. Okay. And when we talk about whether things are odd or even, okay, somebody said it's more like logic gates. Absolutely, absolutely. And that's why it's so important. And, you know, binary arithmetic, mod 2 arithmetic, logic gates, they're all connected. And the mathematics helps us understand how they're connected. Anyway, this is used a lot because, you know, if you're sending data to somebody, there could be a mistake. You know, I just want to say one thing about communication here because it's so important. There are several things that are extremely important about communication. You want it to be accurate. If you're a bank and all the numbers are wrong, either you're going to make piles of money and your customers are going to be angry and quit, or your customers are going to be happy and you're going to lose a lot of money. So you have to be accurate. Okay. The other thing about communication is you want it to be secure, especially if you're a bank, or if you're buying something online and you're giving them your credit card or you're giving them your NIC. You don't want somebody else to be reading that and saying, oh, here's a nice credit card number. I can buy all the stuff I want online. So we want our communication to be secure. Somebody's asking about division, and we'll talk about that in a minute. And the other thing is, and this is particularly important today, like if you're sending messages back from Mars, we want to be efficient. Okay, so these are 3 important things with communication. And modular arithmetic, and I'm going to show you in a minute how you can help, how mod arithmetic can help with accuracy. But mod arithmetic is used for all 3 of these things. Accuracy, we have check digits, error correcting codes. You've probably heard of those. Security, we have crypto systems. You know, that's what cryptocurrency is all about. They have to be secure. If you have money invested, you want it to be secure. And these hashing functions, they're trying to make sure that you have secure communication. The other thing is, with so much information going back and forth, you want to be efficient. And we have, for efficiency, we have data compression. You know, if you're not efficient, you're going to need, you know, 10 hard drives. If you're efficient, 1 hard drive might be enough. So all of these, there's other things they can use as well. They can use geometry for security. There's a lot of things, and accuracy. There's ways you can use geometry for those. So there's lots of techniques for these, and a lot of them use mod arithmetic. So it's a very, very useful thing. Even though mathematicians just started studying it was because it was interesting. It was kind of fun. Now, something I wanted to say about this. Oh yeah, about the security. Well, of course, all of these things, people keep wanting to refine and refine and refine. Error correcting codes, people want better codes. Efficiency, you want to be able to download a movie very quickly. You don't want to have to wait overnight. But security is a huge problem. And as computers get better and better, security becomes more and more of an issue. And with quantum computing, is going to make all the secret codes that people use now, and you may have heard of some of them, RSA, some of the other ones, all of the secret codes useless. So lots of mathematicians are working on what kind of codes a quantum computer cannot break. And it's going to have to require new ideas, new mathematics that people don't have now. And that's just an aside. I just thought it just was one of these things that fascinates me. You know, you have to keep up to date with these things. So anyway, I just want to tell you about the parity check bit. Parity check bit. It's just a bit. You have a string of zeros and ones. Maybe 1, 1, 0, 1, 1, 1, 0. Okay. And you're going to send this. So we're talking about accuracy here. So you want to send this. What you're going to do is put a digit at the end. And you're going to make it so the total number of ones is even. So 1, 1, 1, 2, 3, 4, 5. So I've got to put a 1. Now I have 1, 2, 3, 4, 5, 6. If I have 1, 1, 0, 1, 1, 0, 0, 0. When I look, I go, okay, 1, 2, 3, 4. I'm going to put a 0 at the end. Okay. So it's parity. Parity is odd or even. And then I have, I think, I don't have any examples. Okay, so you tell me, I'm using a parity check bit, and you receive this message, and then you receive this message. And then you receive this message. Okay, so let's call this A, B, C. Okay, so I'm telling you, I tell you before I send the message, I say, I'm going to use a parity check bit. And I send you these 3, so you know I was using a parity check bit. Was there a mistake in the transmission here? What do you think? Raise your hand if you think this was sent correctly. Okay, I'm seeing lots of hands raised. Yes, this is correct. Now, it could be that 2 numbers were made incorrect, but the chances of 2 being incorrect is pretty big, because first of all, we have to make sure we have a decent communication channel. What about this one? Raise your hand. Okay, you can put your hands down. Raise your hand if you think this one is correct. Is this one correct? Uh-oh. Uh-oh. I'm seeing hands raised. Is this one correct? 1 0 1 1 0 1 1. It's wrong. Some people in the chat are saying wrong. This is wrong. And the reason it's wrong is because there's an odd number of ones. Okay. So the people in the chat are correct. And then, is this one correct? What do you think here? Wrong again. Okay. So if I got this message from you, what I would do is I would respond and I'd say, this is what I got. Something's wrong. Please fix it. Okay. So that's what we do there. Now, okay, so someone is asking about division. What is 1 1 0 0 1 0? Okay, so 1 1 0 0 1 0. If I got this, if you sent me this, and I knew that you had to add a parity check bit at the end, I'd say some. Well, you know, there was a transmission error. Okay, a transmission error. Okay, so what these are. Okay, let me be. I'm not sure I was completely clear. This is a string of numbers that you send me. And we've agreed ahead of time that you're going to, or it doesn't matter whether I'm sending or you're sending, but we agree ahead of time we're going to use a parity check bit. And okay, what does it stand for? Okay, I don't know. I don't know. I just made this up. I don't know what it stands for. Okay, because it's like, this is some number you're sending me, some piece of information. You know, you write you have a computer form online, and you get, you know, you ask somebody, you know, what their age is. So some of the digits are for the age, and what their gender is. Some of the digits are for that. You know, are they a member of the club? What's that? So I don't know what these stand for. I'm just talking about these are numbers that somebody might get. Okay. So division here, I don't want to talk about division here because it's a little complicated. But what I want to do right now is Mod 11 arithmetic. And I want to do this for a couple of reasons. One reason is because it's different from Mod 12. It's also different from Mod 2, but it's harder. But it's also used, so I want to show you how it's used. And so let's fill it in. Okay, 0 and 0 is 0. Mod 11 is going to have 11 numbers, but they're only going to go they're not going to go to 11 because we have the 0. So when we have 0 thrown in, we have 11 numbers. Okay, and again, this is a finite arithmetic. And I hope you're filling these in while I'm talking. It's a finite arithmetic, but the infinity comes in because we have one of these arithmetics for every integer. And I see some of these questions, and I will get to them. I know it sounds strange, but in my doctoral dissertation, I used Mod 2 arithmetic, and that's all I used. I didn't have to use any other kind of arithmetic. And so all the answers in my dissertation were either 0 or 1. Now, to get the addition, it's really easy because I know there's a pattern. It's going up by 1 each time. But of course, when I get to 10, the next one isn't 11, it's 0. And when I add 6 and 6, I'm not going to get 12, I'm going to get 1. Oops. It's real easy to make a mistake with this because you're so used to regular numbers. Oops, I made another mistake. I'm still thinking mod 12, 10, 0, 1, 2. Oh. Okay, now the multiplication. Remember with mod 12, we said if we have, yes, somebody's saying again, we can see the diagonal. Okay, we see the diagonal pattern again. Exactly. We're going to see that. Now, with mod 12, we remember that 2, 3, 4, 6, 8, 9, 10, we all had repetitions because those numbers had a common factor with 12. Here, it's not going to happen. And the person who asked about division will be able to say something about that once we've got this table done. I think the easiest way to do multiplication is repeated addition. So here, I'm going to add 2 each time. 10 plus 2 is 11, but that's going to give me, no, 10 plus 2 is 12. Sorry about that. It's going to give me 1. And then I'm going to do this down. And I know multiplication is commutative. So if I have a row, I can do the column. What I'm doing is I'm adding 8 to 7. I'm not multiplying 8 by 6. It's much easier that way. Okay, good. Okay. 8 times 5 is 40. 8 times 5 is 40. But we're in a clock with 11 hours. So 33 is the same as 0. So 40 is the same as 7. Okay. So can I teach you easy ways to calculate? Well, I'm not so sure that I can, but I can teach you a way. When we do Mod 10 arithmetic, we'll learn a way to check things, check arithmetic. But for this, the easy way to do it is not to do 8 times 5 is 40, but to look at 8 times 4 was 10, and then add 8. That's, that's how we get, 8 times 4, and then 8 times 5 is 8 times 4 plus 8. That's just our distributive law. Okay. Now there's one important thing I want you to notice about this. And that is that every row well, let's not put it that way. Okay, every row, somebody put it in here, every row and column contains the digit 1. Okay, now what that means is, let's look at an example. 8 times 7 . Now, if you remember how to solve equations, when you had, this is regular arithmetic. Over here. If you had 2x equals 8, what's x? 4. Somebody got that right away. Samudra. So that was easy. You just divide both sides by 2. Now here, let's suppose I had 8 times x. I don't want to put times x, that's confusing. So what if I just have 8x equals 4 mod 11. Suppose I have this equation. Here we divided by 2. I'm not going to try to do division here because I haven't defined division. But we know this. This is very helpful. And with equations, we know that whatever we do to one side, we can also do to the other side. That's that's what equality means. So I'm going to multiply both sides by 7, and you'll see why in a minute. What's 7 times 8? Well, okay, I had 8 times 7, but multiplication is commutative, so this is just x. And now what's 7 times 4? I'm going to go look at my table. 7 times 4 is 6. So I've solved the equation. With mod 12 arithmetic, I couldn't do that. If I had, let's see. Okay, I'm going to erase some of this stuff because I need room. If I had 9x equals 8 mod 12, can I solve this equation? Can I solve this equation? No. Because look here. There's a couple reasons. 9 times something. 9 times 1, 2, 3, 4. You're never going to get 8 in the 9 row. But it's also because there's not a 1 there. If there were a 1 there, like in the 7 row, if I had, 7x equals 8, I can do it. I mean, one way is I could kind of cheat and I could look over and I'd say, oh, well, 7 times 8 is 8. So x is 8. Or I could say, well, let's see, where's the 1? 7. Okay, so multiply both sides by 7. Multiply both sides by 7, and I get 7 times 7 is 1. And then 7 times 8, I get 8. Okay. Okay, but anyway, I don't want to get caught up in solving this because I want to show you how it's used. Now, if you look at a book, and I've got a book here that I just found on my bookshelf, but let's look at a book. Let's see. Okay, here's a book that I wrote, so I think it's cool. So it has a number on the back. Let's see if I can show you. I can't see my camera here. Oh, there I am. Okay, so in the back of the book, let's see where it is. Right there, there's a number. Okay. Now, they started having 13 digits, but I'm just going to look at the 10-digit number, and I'm going to copy it here. And let's see, let's go all the way down. Oh no, let's just go here, right here. So I have 1 dash 4 3 5 4 5 6 5 6 dash 4. Okay, so that's the ISBN. It's International Standard Book Number, and every book that you get by a publisher will have a number like that, and it helps. You know, if you're shopping online and you go to a bookstore online and you know the ISBN, you can find the book here, because a lot of textbooks have a first edition ISBN. We know they're going to get the right textbook if they had the number right. See, I don't know about you, but when I copy a number down, sometimes I make a mistake, and the most common mistake is called a transposition. And that means maybe I'm copying this one 5 6 5 6. I might copy 6 5 6 5. Trans means across, position means, you know, where it is. So I can interchange 2 adjacent digits. Now, if I give you the number wrong, you're going to get the wrong book. You're not going to be happy. So these numbers have parts to them. This number says English. This number is the number that the publisher has. You know, some publishers have more than one number, but this is the publisher number, and this is the particular book number. Okay. What's this? That's a check digit. And how do we get the check digit? Well, what we do is we use mod 11 arithmetic. We multiply this one by 10, this one by 9, 8, 7, 6, 5, 4, 3, 2, 1. We add them up, mod 11, and if we get 0, we have not detected an error. Now, we're not guaranteed that it's the right number, but because most mistakes are going to be 1 digit off or transposition, you know, you might do a 6 instead of a 5, especially the way I wrote my 5. So if that happens, then this will detect it. Okay. So let's see if I have the right check digit. If I've made, yeah, I mean, I could have copied this incorrectly. So let's do it down here. I've got some room. So 1 times 10 is 10. 9 times 4 is 36, but I'm lazy, so I'm going to do this part in my head. 9 times 4 is 36. Mod 11, so I subtract 33, so I've got 3. 8 times 3 is 24, so I got 2. 7 5s, 35, that's 2 more than 33. Huh, 6 4s are 24, I'm getting all the same numbers here. 5 5s are 25, so that's going to be a 3. 6 4s are 24, that's a 2 again. Oops, this is a 3, 15, so that's a 4. 12, that's going to be 1, mod 11, and 4. Now, I hope this adds up to 0. So I'm going to be lazy. One of the things mathematicians are, they're lazy. Okay, I know that 3 and 3 and 3 and 2 add up to 11. So that's going to contribute 0. I know 10 and 1 add up to 11. So that's going to contribute 0. Let's hope the other one's 2. That's 4. 8. And that adds up to 1. Is that what it's supposed to be? Uh-oh. Uh-oh. I made a mistake. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Uh-oh. I made a mistake, and we have to find the mistake because I'm going to feel terrible if I made a mistake. That's why we have computers. 1, 4, 3, 5, 4. 5, 6, 5, 6, 4. Okay. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Does anybody see a mistake? 7 times 5 is the mistake. Okay, thank you. So 7 times 5, this one is 35. And that should have been a 3. This one here? Is this the one? Or this one? Let's see. 10. Okay, let's see. 10 times 1. 9 times 4 is 36. That's 3. 24 is 2. 35. So this should be 2, right? Okay, yeah, thank you for pointing that out. This is the one. Okay, now I can do my lazy man's way to add numbers up. This was 10, this was 2. Okay, so this and this add up to 11. The 3 and the 3 and, oops. 3 and 3 is 6. Oh, that's not going to work, is it? Let's see. Okay, here's 11. That's 11. 3 and, 2 and 2 and 2 is 6. 9 and 2 is 11. And then these add up to 11. 3 and 7 and 11. Okay, so what we have is it adds up to 0. So we don't find a mistake this way. Oh, 6 times 4? Did I do that one wrong too? 6 times 4 is 24, should be 2. What did I put? Uh-oh. Okay, you know what I'm going to do. I'm just going to start all over again. That's what, whenever I get too many mistakes, I just say start over again. 1 times 10 is 10. 4 times 9 is 36, that's 3. 3 times 8 is 24. 22 is 0, so that's 2 more. 35 was 2. 6 times 4 is 24. So that's another 2. 25 is a 3, another 2. 15 gives us a 4. 12 gives us a 1 and a 4. Okay. So I've got a 10, I've got my 11 there. And then 6 and 5 is 11. And 8 and 3 is 11. Okay, so yeah, this checks out. This is correct. Thank goodness. And then, oh, the reason I chose this one, now I remember, was because, oh no. This was just an example. It was a book. And, okay, sometimes the check digit has to be 10, it turns out, and then you use an X. And, you know, I could probably look at 20 books and not find one with an X. But if you look at your books that you have, you might find one with an X. No, I don't have any with X's that are handy. Okay, so you just use an X for the check digit. Now, okay, do you think you understand this? Raise your hand if you understand it. Okay, I'm getting a lot because, well, I think I'll make you do this anyway. So we have 2 questions here. One is find a check digit for an ISBN. So in other words, maybe 0 and 1 are both English. Okay, so these are probably English books as well. And here's it's publisher 12 and publisher 486 and publisher 13. And then this is the title of the book. And what I would like you to do is find the check digit. Okay. And when you tell me in the answer, can we convert it to another mod? For this, ISBNs are mod 11. That's just the way it is. Now, the second problem, I don't know why these numbers are here. These shouldn't be here. If you give the answer, put it in the chat, but put A with it. So A, put like 1 or X or whatever. But so somebody says, can we do a different mod? And so I'm saying no, because the International Standard Book Number Association said we're going to use mod 11. For the 13-digit check, the 13-digit one, I don't know. They might use a different mod. I'll have to check. I haven't checked on these recently. Anyway, but here's where you can use a different mod. You have club members, and each one has a 4-digit membership number. And you're designing barcodes for the membership cards. What I would like you to do, and this it's not like there's a right answer. There's lots and lots of different answers. Create a check digit scheme. And I am sure that your student numbers, there's a check digit thrown in there somewhere. I don't know how you would find that out. Maybe the director of student services might know, or maybe it's buried in the computer. But I'm sure that your student number has somewhere a check digit. So what I'm asking you to do is create a new scheme, and you can use whatever mod you want. You can use whatever addition you want. You can have, and I'm saying a scheme, you can have 2 check digits. You can have 5 check digits, whatever you want. So I want you to be creative. So let's see. Yeah, I don't know about your Solochana said, can we convert it to another mod? So you can create another mod here, not here, but if you want to use another mod, this is where you do it. Okay. I'm getting different numbers for these, so I'm going to have to do it myself and hope I get the right number. I wasn't doing it before. Okay, I'm not sure I was clear. What has to happen is that it's not that this is the sum of the other ones. It's when you put this one in, you end up with 0. So in other words, 0 times 10, 0, 1, 2, 1, 2, 8, 8, 5, oh, and here's the check digit X. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. When we do these multiplications, these add up to 0. If you know anything about dot product, if you did anything in physics, sometimes you do dot products. This is 0, 9, 10. Oh, wait a minute. No, that's not 10. 1 times 9. 2 times 8. That's 16. 7, 12, 40, 32, 8, 2x. And I'm doing it out the long way here. Okay, now I'm getting the right answer. Yeah. Okay, and I'm going to add these. I'm just going to do 2 at a time, make my life easy. Eight and 3 is 11, so that's 0. Ew, I did something wrong here. Does anybody see what I did wrong? Uh-oh. 9, 1, not 8. Nine, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 0, 1, 2. 1, 2, 8, 8, 5, 0. Oh, yeah, this is it. This is it. Thank you. But I still think there's another mistake. Okay, 0. Okay. 5 times 3 is 15. Oh my God. Five times 3 is 15. So that's 4. Okay, phew. Now I think I've got it. Okay, so we've got a 0, 0 plus 10 plus x. We want that to be 0. What does x have to be? X has to be 1. So it's not what you get when you add up the numbers. It's what you get when you add up the numbers and say, subtract that from 11. Okay. And so let's see. B, okay, let's see. 6 and 2. Oh dear, I'm getting different answers. Okay. People are telling me 6 and 2. Well, I've got 6 and 3 and 2. A 9 and 10. Oh dear. Okay. And I'm getting a 10 here and an 8. Oh dear. Okay. Okay, you know what I'm going to do? We're running out of time. I think what I'll do right now is I'll check these two so that we do have the right answer. And then if you have time between now and tomorrow, if you could, I've got 102. Oh my gosh, these answers are all over the place. I think the first one is 1. Anyway, if you have an idea for this one, and I'm going to erase this so I don't have it in the way. If you come up with a scheme, you know, you can use your imagination. And the people that did the ISBN said, well, we think people are going to transpose digits. You know, maybe they do some other things with the numbers. Who knows? 0, 4, 8, 6, 6, 5, 6, 3, 3. And then we have this check digit here. And we're going to multiply it by 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Now, I'm going to be real careful about my multiplication because that's where I goofed up before. 0. 36 is 3. 64, that's going to be 9 because, I mean, I can even check it. I've got my table up here. 8 8s are 9, yeah. 6 7s are 42. So that's 33. So that's that. It's hard to do stuff in your head when you're 6 times 7 is 9. Oh yeah, that's what I was thinking. 36 is 3, 25 is 3, 24 is 2, 9 is 9, 6 is 6, and X. Okay, now I'm going to do my, that's 11. Oh, I didn't do casting out 9s. Let's see if I can do that. Okay, I'll just one more thing. 3 and 9 is 12, so that's 1, 1, and 3 and 6 is 9, 9, 10, 11. So it should be 0. So yeah, I think this is 0 for this one. Okay, I just want to show you one last thing. Medusha tells me we can go on forever, but I know that's not really the case. Let's do a multiplication problem. Let's do 8 times 8. That's 64. Oh dear. I'm sorry. This is the wrong table. I wanted to do mod 9 arithmetic. So just pretend this one isn't here. If you've got your Excel spreadsheet open, just delete these things here. Now 64 is 6 times 10 plus 4. And 10 is 9 plus 1 plus 4. Nine in mod 9 is 0. So 64 is 6 plus 4, or 10, or 1 mod 9. We'll review this tomorrow. I'm going to go through it quite quickly right now. But in mod 9, to reduce a number, you just add the digits together. If any of you are interested in numerology, that's what they do in numerology. They add up the digits. And you keep adding them up until you get something less than 9. And you're casting out 9s. In other words, you're reducing mod 9. And this is a way to check computations. This is what I wanted to show. Suppose you multiply 46 by 8, and your answer is 368. 46 is 1 mod 9, because 4 and 6 is 10, 1 and 0 is 1. 8 is 8, because it's already less than 9. 3, 6, 8, how do we get that mod 9? 3 and 6 is 9, and 8 is 17. 1 and 7 is 8. Okay, and so this is like, if this were in mod 9, this would be 1 times 8, 8. It's all right. Now, we may have made a mistake, but the mistake is off by a lot. But here, 95 is 5 mod 9. 1 and 3 is 4. 368, same number. It's 8. And now we look at the multiplication. 5 times 4 is 20, but 20 is 2 mod 8. So this product should have been the same as this one, and it's not. So it's a mistake. Okay, we'll review this again tomorrow. Yeah, somebody said 2 mod 9. So what we did today, we reviewed set theory. We're going to review the cardinality of the real number line again tomorrow. Actually, I don't think we did that. We just did the those irrational numbers. But we'll review that again tomorrow. And we can review this as well tomorrow. And if anybody has come up with a check digit scheme for 4-digit membership numbers, maybe what you can do is put it in the chat at the very, like right before class. And I'll look at the chat right at the beginning of class, and we can see if we've got some good membership schemes. Somebody says, can I share the PDF notes? You should have gotten those. Okay. Can you share the PDFs? Yeah, you should have gotten them. So if you haven't gotten them, check with the person that's supposed to send them to you. Now, okay, I'm on OneNote. And I should be able to share all of this with you. I will see, I know you have, it's been recorded, you'll get the recording. So you'll have it there, but I think I can share this whole thing with you. And so what you would get is everything with the notes on it. So I'll see if that, but you should have the PDF. And somebody says that you, Sanuga says you have this. Oh no. Mahomed says we have it. Oh no, tomorrow. Okay, somebody asked about uses of other mods. Let me see. UPCs. I got to find something I bought that has a UPC on it. Yeah. Here we have a UPC. Can you see it? It's not coming through clear, but this UPC, the last digit is a check digit of 4. All I have are books. I don't buy anything but books. Something's wrong with my life. I don't even have a candy bar. Let's see. I might have something in the kitchen. I'll be back. Okay. Yeah. Can you see this? I don't see it very clearly. Okay. So if this is a UPC, Universal Product Code, and they put it on you know, when you scan things in, and it has a number at the beginning, and then it has a number at the beginning. I can't remember what that is. It just like, I think 0 means common products. And then it has a company, the producer, and then it has a product number, and this digit hanging on the end here is the check digit. And this uses mod 10. And instead of multiplying by 11, 10, 10, 9, 8, 7, 6, it's 3, 1, 3, 1, 3, 1. So all barcodes are not the same. If you had a company and you wanted to have employee IDs or product, inventory control, something like that, you would have to create your own check digit scheme. And that's why I gave you this problem with the club, the membership number. The recording, I don't know how you get the recording, but I know it's been recorded and you should get it. Okay, so tomorrow we're going to do Mandelbrot set. If you want to drop out now, I think it's okay because I'm really done. But, okay, you know what? I'm going to give you a taste of what we're going to see tomorrow. Let's see, where is it? Okay, I'm just showing you this because you're still here, not because this is part of today's lesson. Can you see this? Raise your hand if you can see this. Okay, good. So this is what we're going to talk about tomorrow. This is the Mandelbrot set. And one of the themes we've had in this course is infinity, and this for sure has infinity. And we'll learn tomorrow how this is computed. It uses complex numbers, but it's actually extremely simple. So I would just want you to be here tomorrow. Okay. Okay, what is the mod that usually using for right? I don't think there's anything usual about it, about usually for check digits. If it's UPC, it's 10. If it's binary parity, it's mod 2. If it's ISBN, it's mod 12. It's mod 11. I think the mod 13, the ISBN 13s, I don't know whether they're 13 or 11 still. But, okay. So anyway, this has been fun. You know what I'll do? I'll put the URL for this in the chat. And if you want to watch it, you can. So I'll see you tomorrow, and good night. Okay, so I'll see you all tomorrow. Bye-bye.